So, just to finish or to give you the last informations, due to the CTOD, I've found yesterday again a small video where you can see, okay, how is a fracture toughness test performed. So before you saw, okay, like the Sharpie test where we did the recalculations of the fracture toughness K1C due to the fracture toughness. And this is like a fracture toughness test, a real fracture toughness test, where you see, okay, at first you start here, you do some crack, some cyclic loading, the crack is growing, and afterwards here you start to apply the forces and the stresses, and you at the end get here the information about the stress state and also about the plastic deformation. And so yeah, so but now I want to go into the evaluation of some fatigue tests. So again, which color is better to see, the red or the blue one? Okay. So when we started the program, we mostly talked about the SN concept, which is widely known as the nominal stress concept. So therefore, we have done some basic calculations last week where we just used here the curve with some information of NC, which is 2 times 10⁻⁶, and our delta sigma C, which at the end defined our notch class for a specific detail. So, but of course, the question at this level is also how is, for example, this notch detail defined? Of course, there we run a lot of testing, a lot of different specimens were tested, and at the end, in some committees, they decided, okay, this is the notch class which will be applied, and this is at the end the information which is provided inside the codes for the companies, for the designers, and which is at the end also somehow the most important information we have due to the fatigue assessment. So, of course, for example, we have here our specimen. So the specimen just in a pulley done small specimen test is looking like this. So we have here the B at the clamping, we have here the B0, and of course we have a width or a depth, which is the A0, and at the end have some different definitions about the curvature for specific material testing. But for example, if you just go for some basic curves in our SN curve, we also can use here the tension test bores. So, and at the end, this here is loaded, by just on sinus. So we have here our ft, and the ft is defined over f0 times sinus plus f1. So we have some mean value. And here we have our amplitude. So, English, sorry, small a. We have the amplitude. So, and at the end, this is how we're gonna conduct our testing. So we have at first our first informations of what we want to go into our concept, and then, for example, for an R value of 0.1, we have here a time force curve, which is just going upwards, downwards, and afterwards the sinus is started. So, and at the beginning, we just have to go and apply this testing procedure onto our specimen with our defined mean value level, F0, and here F1. So we have here our mean value, and here our amplitudes, and at the end we test this specimen until failure. So when the specimen is broken into two pieces. So we have, due to the theory, we have here the time of the correct initiation, and also the time of the correct growth. And at the end, this specimen fails. So if we go into the production of our specimen, we have a little bit, to look onto the roughness. And because the roughness, as you can assume, the roughness is describing some property of our surface. And if you go now into the microstructure again, and you go into the roughness is something which is looking like this. So, of course, now we go for cycling loading. We talk about cracks. We talk about correct initiation, and then, of course, these points here, always some cracks or some surface cracks in the micro surface at the surface. Sorry, and due to this, of course, the roughness has some influence on the testing itself. So, for example, usually if you go and you have some quality informations on the steels you're using, and so if you have some drilling or some miling, usually you have to take care on the surface and also on the roughness of the surface. So at this level, you also have to think, okay, which roughness you want to have, and also if you go there. Sometimes, due to the drilling or due to the mining, you can have here at the curvature some point of resting of the production machine. And so if the production machine rests, you get here some notch. And this is also something which you have to be care on if you do like a specimen or some production of the specimen, just to be sure that you have a quality of the roughness, that you have no inclinations or no notches on your specimen as well. And so at the end that your specimen is showing you the same behavior and the same material properties, but also production properties as your structure at the end. Sorry. Okay. So, and so at the end, we have here some situation where just we have a failure. And our specimen is broken. So, and therefore, okay, we now can make a table, and the table at the end looks like this. So, for example, we have testing 1, we have an amplitude of 240, we have a mean value of 0, so due to this, we have an R, which is -1, and at the end, we also want to know our cycles. So, for example, for the first testing with 240 MPAs, we got a failure after 26,200 cycles. So, also what you can see here, it is here also rounded to a number of 100. Because due to the logarithmic definition of our SN curve, the last number doesn't really go into count for the huge numbers you have here. So this is why, for example, here you have also some assumption there is, for it is depending on the laboratory sometimes that they say, okay, they don't go and deliver the real amount of numbers, because here this is something which is at the end not important for the calculations of the SN curve. So, and so, okay, this is the testing procedure at the first level. So, and so the next is that you have to assume a frequency. So here, which is a huge omega. And the frequency is something, of course, in hertz. And this is just some information you have to give to your testing machine, and also at the same time, of course, it has to be something which is depending on your structure. So, for example, in our case, we usually have something which is, due to the codes, between O and O hertz. Doesn't really seems 1 hertz and 40 hertz. So, but the 40 are also quite high. So, with the measurements we have, for example, in our laboratory, we go to 10 to 15, but then it's the machines cannot handle higher frequencies. But also, there exist some testing laboratories where we go up to 160, 200. So, it's, if you have the right equipment, you can do a lot. So, and what is at the same time, as we already talked a little bit about, is the different concepts we have. So, for example, you have the high cycle fatigue concept, you have the low cycle fatigue concept, and you have the very high cycle fatigue concept. So the LCF, it's or the switching between the LCF and the HCF is in the codes it's around 10/4, and this is around 10/7. So, and by applying an R value of 0.1, we always go, or as we do our procedure, is that we use some horizons. And at these horizons, we always apply 3 to 6 tests. And so at first, we have to define our first horizon. And the first horizon is here around 0.8 Fy, 0.6 Fy, 0.4 Fy. So this is some stepping or 3. But the steps are also somehow depending on the stress ratio you apply on your machine, or you apply on your system, you apply on your during your testing. So as you can see here, we are still in the elastic, or we want to have just elastic behavior, and at the end, due to the elastic behavior, we of course can calculate here our stress range, which is always F/A, and at the end, we can calculate our delta sigma. And the delta sigma is at the end the value which we have here. And at the same time, if you now go for the tests, for example, we have here N1 and here delta sigma 1. We have here N2 and 3. So this is, for example, our first horizon. And if you see here, the first horizon is going here from testing 1 to testing 6, with always a stress amplitude of 240 and a stress range of 480. So, and how do we analyze? So how do we analyze at the end our fatigue curves? Is there exists different methods. So for example, here I used just the correlation analysis. So we want to use still the law of Pascaline, and this is at the same time defined comparable to the correct propagation of pairs. So we have here our LGN is VA So looks like this. So it is a linear curve which describes in a double logarithmic space at the end the regression curve, and so the mean value of our testing. So, and at the end, what are we doing? It's just a linear regression analysis due to the testing, to the tested specimen. And also we have to go there and define the standard deviation, and at the end can shift to some specific values we want to analyze. So in this case, for the linear regression, I used here the correlation analysis. And with this, I get here my 50% curve, which describes here the mean value. So what I'm doing is, for example, in a quite easy explanation, but which does not fit to the analysis I've done here, is that I go here, and for example, in the case when I already know about the slope, I know the slope of my 50% curve, so I can move each point to a specific level. And so at the end, I just describe here the standard deviation, the logarithmic standard deviation. And so with the logarithmic standard deviation, standard deviation, I can calculate the mean value and also, no. This is the log normal distribution. And so I have here the mean value and the standard deviation. Sorry. And so due to the standard deviation, at the end I can calculate here the value of the 95% of the failing. And this is also the level, for example, we used in our codes, that we say, okay, with the 95%, we have a good, this is the reliability concept we are working. So we said, okay, this is the mean value, and we don't want to talk about this area, we just want to have the 5% of the percentage which gonna fail during our life, and the 95% are failing above the defined curve. So at this time we have to shift here also our our mean value. So usually you have to go there and define a value k, which is depending on the amount of specimens, times the standard deviation, and here you have the 50% value minus, so the mean value minus k times s, and this is also the k in the practical assumption is usually defined by 2. So, and this is at the end what is basically done if you go for the elevation of a fatigue test. That you say, okay, of course you have to define your law, So your engineering law, which you want to apply. So this is here our curve of Pasquin. And also at the same time, you have some reliability concept, some failure assessment where you say, okay, this is the mean value you have due to your testing, and then you shift your curve onto next to the safe side, and you have to define here a quantile value to give you, at the same time, some information to have a good estimation due to the design in the first level. So, and for example here, when we say, okay, we don't want to go and give a first, or if you don't want to have the information of a fixed slope definition, for example, then we go there and use the correlation method or the maximum likelihood method. And this is what is done there, basically. So at first, we have to calculate our logarithmic values. So as you can see here, we calculate the xy, which is just the logarithmic of the the log of the delta sigma. Then the yy is the log of our number of cycles. Then the next information is the square of the x and the y, and also the multiplication. So at the end, we just have to sum up all informations, and then due to the correlation analysis, we get here our slope, which is just defined by this formula. And also we get here the intersection of our curve with, in this case, the x direction. So this value here. So this is a little bit different to the functions you usually gonna calculate, or for the regression models you usually apply. Because if you go there and say, okay, you go for a regression analysis, you say, okay, you define something which is y over x. And so in this case, we have here on this side the log n, which is here our x and not the y. So, and that's why this formula is a little bit modified due to the usually correlation method to get here not the information due to the intersection of the y-axis, but due to the x-axis. Because the usually correlation method would give you this point, so the y intersection, but for our Pasquin model, we have to get this point. So, and due to this, now we have our two values, and of course, we have now defined our law of Pasquin, so the log A, the m, and the log sigma and the log n are two basic informations. And also, we can, due to the correlation method, we can calculate our standard deviations. So the standard deviations are here given in a two-dimensional way. So if you take this point out, we have here our 50% curve. we have here our dots. So this is our fatigue testing information. And we have here our log normal distribution. So at the same time, we have here, which is due to the statistic, usually the mu with the 50%. And this is the information for a specific log n and log delta sigma. So just got from this diagram to a specific point. And so we can calculate a standard deviation into this direction, which is here the SYY. We can calculate our SXX and also the SXY. And at the end, we want to shift like this, so that we have in our resistance model contributed the variability of the delta sigma and also of the cycles. So, this curve is. So, but as you can see, all points have to be on the same line. So, but just to have at the end the correct definition of our point delta sigma c and nc, we have to use here this point. So, and this is particularly what is done if you see such a curve. So you have here, due to our parameters, you can give or define your resistance curve, so in a straight line. So for example, for your 5,000, 5 times 10 over 3, 10 over 4, 10 over 5, 10 over 6, 5 times 10 over 6. You can recalculate your delta sigma values. So in this case, this is the blue line. This is our 50% assumptions. As you see here, our fatigue testing dots are on this side. So for example, and of course, you have also here the shifting due to the standard deviation. And at the end, sorry. And at the end, your notch detail, which you define, for example, is this point. So you have here your 2 times 10 over 6. So you have here your 2 times 10 over 6. And at this point, at the end, you have you can get the information about the stresses. And this is at the end according to a specific stress ratio, which you have applied during the testing. The notch stress, which is according to your model, specific to the tested detail. And at the end, for example, you have usually some scaling or some equal distances between the notch details so far in the European codes. And so, for example, for this specific detail, you have here a value which is around, if you go inside, around the 180 MPa. And at the end, you have to recalculate it to the stress ratio of 0.5, which is related to the codes. And then you would end up for a notch detail of 160, which also gonna fit to the tested material, which was here. Just specific tension flat bar, and did not correlate to any valid part or something else. Okay, so this is what is basically done to evaluate the testing in the high cycle fatigue area. For the very high cycle fatigue area, I could not find a good example, actually. Also in our database. But what is going forward? So as you can see here, the tested cycles are here still above the 0.10 over 6. So if you still decrease the stress range, you get here to a level where you have some tested specimen which are not going here. So at the end, they're gonna end up at this level. So what you have to do if you want to look on the point of the durability of the fatigue strength, you go there, you test here, and if this point, for example, the material or the specimen doesn't fail at the level of 10.7, you increase again the just tested stress range. And so at the end, by increasing, decreasing, you get here some specific values. And at the end, you just can do the same as before, but you just talk about the stress range. And you don't care about the amount of cycles. And that's how, at the end, you can define also the curve with the horizontal plateau, just to get the informations on where do you not have any, or beyond which stress state, stress range, you don't have any failure in the material, theoretically. And so at the end, you have defined at this level the value for HCF and VHCF. And for the LCF, you have here usually a plateau, which is defined by Fu, which is just 1 minus R, so which is given by the tension, the ultimate tension strength of the material, and of course due to the definition of the stress range. You have also have to take into account to get here the recalculation from a value which is at this level due to the Fu defined by the sigma max, so of the maximum peak in the testing, and at the same time to the related system in your SN curve, which is here defined to a stress range. So yeah, so this was quite fast. So this was basically the fatigue evaluation procedure you have and how it is gonna be applied. We have time left, so are there some questions? Okay, otherwise, thank you for the attention. And let's start tomorrow with the last program topic, which is the load investigation. And so on how we end up from information like this to information on this. So this is also something yeah, I want to go tomorrow into it. And then I think we have done quite most of the important topics to have knowledge about the basic concepts and yeah, to have a little bit fun to work on this topic. Okay, then thank you very much and see you tomorrow.